So again, collecting together questions across the organic syllabus, this time just the various tests. As is usual, when one is pulling out the questions from the A-level, some of the questions are just parts of questions, so there might seem to be bits in there that don't make sense. Don't worry about those. And then, of course, there will be bits in the questions that aren't exactly associated with tests, but serve, first of all, as part of the big question, and secondly, to enable you to review some of these things. Anyway, given a pure sample of this compound below, asked to carry out some reactions with it. Sample is added to aqueous sodium hydrogen carbonate. State what's seen during the reaction. Well, it's the acid group, the COOH, that reacts with sodium hydrogen carbonate to give effervescence, the production of CO2 gas. Good test for acid groups. 3-amino propanoic acid, compound X, isomers compound C3H7NO2. However, only compound X produces a silver mirror when reacted with Tollens reagents, suggests a displayed formula for compound X. Well, the first thing is anytime you see a formula, add up the number of hydrogens, compare it to the number of hydrogens that should be there, and that will give you the degree of saturation. 3 carbons have 8 hydrogens, and nitrogen gives you another one. So we expect 9 hydrogens for 3 carbons and 1 nitrogen. That's only 7. So we have 1 double bond or 1 ring somewhere, 1 degree of unsaturation. The Tollens reagent tells us that we've got an aldehyde in there. That's a great test for aldehydes, the Tollens reagent silver mirror, and that is, of course, the double bond there. So what we need is just to come up with a displayed formula that contains the appropriate atoms and an aldehyde group. So lots of possibilities there, because once you take the aldehyde group, the CHO out, you've got C2H6 and NO left. So we can do it as alcohol amines with various bits swapped around. We can have primary amines, we can have secondary amines, we can have alcohols, or we can have ethers as far as using the other nitrogen. So 2,4-DNP, there's 2,4-DNP dinitrophenol hydrazine, can be used as a reagent to identify aldehydes and ketones. State what's seen when 2,4-DNP is used to identify an aldehyde or a ketone. Of course, here you have an amine, which react with the carbonyl groups of aldehydes or ketones to give you this imine right here. And this is a solid. That has, obviously, as most pure solids do, a very sharp melting point that is diagnostic of what R1 and R2 are. You can also get a little bit of a clue for colours. Typically, if R1 and R2 are aromatics, then it's a red-orange precipitate. Alternatively, orange-yellow precipitate if R1 and R2 are aliphatic groups. But the big thing with them, not just to identify, hey, we got a precipitate, but it also enables you to identify what R1 and R2 are. Very useful, important test. And of course, it doesn't help that 2,4-DNP is one of those compounds that administrators know about as being potentially dangerous. And so that freaks them all out about those nasty chemicals. Anyway, I should get off my political soapbox and do the next question. Nice simple test that will distinguish between pentan 2-one and 1-phenylbutanone. So you can see in both cases we have ketone groups, and so they would react the same with your typical ketone test. However, what we have in pentan 2-one is we have this CH3C double bond O group, which has a very diagnostic reaction in the iodoform test. Iodoform test where we take this group, react it up with sodium hydroxide, usually at least hydroxides, and some iodine. And we first of all make this species here, in which we have substituted the H's by the iodine. We then take that, heat it up in base, and we make the iodoform CHI3, which is a nice yellow precipitate, combining yellow and solid to get yellowed, but anyway, yellow precipitate there. Why will 3-hydroxypropanoic acid not undergo the triiodomethane or the iodoform reaction? Because there's no CH3 C double bond O group. This would work because that CH3CHOH can, of course, that's a secondary alcohol, which can quite happily be oxidized to a ketone and thus obeys the test. Acid F was known to be one of the following. I think this is the third worksheet in which we've talked about acids 1 and acid 2. But anyway, how would we distinguish between acid 1 and acid 2 in this case? Well, we look at acid 1. It's got a C double bond C, an alkene group. Acid 2 does not. And of course, an alkene group, relatively straightforward to test for. Bromine water goes from brown to colorless. And acidified permanganate goes from purple to colorless as well. Two nice tests for the alkene group. Okay, now we're talking about reactions of phenol. First of all, take phenol with iron 3 chloride, and what happens is that the phenol makes a lovely little complex with the iron. You can have one phenol on the iron, 2, 3, and so on, and then depending what else is on the phenol, you get different colors, products, but the important thing is that you go from this sort of yellowy orange color of the FeCl3 to a beautiful red, blue, violet type color for this complex. Add sodium hydroxide. Well, of course, phenol is a weak acid, so you add a strong base to it and you'll get a neutralization. And whenever you neutralize a weak acid, you make its conjugate base. So there's the phenoxide, which will of course have a sodium salt. I'm not really going to see a whole heck of a lot here, except for a slight increase in temperature, because all neutralizations are exothermic. Dihydroxy Benzaldehyde right there has the same formula as 2-hydroxy benzene carboxylic acid. Suggest a simple reaction or give a positive test for 2-hydroxy benzene carboxylic acid, but not 2,3-dihydroxy benzaldehyde. Should give the reagent used the result of the test with the acid. Well, anytime you see an acid group in there, you know that it's going to react up with bicarbonate or sodium carbonate to give CO2, which you see as bubbles or effervescence, to use the nice word. Friedel-Crafts reaction carried out with ethanol chloride. Instead of 1-chloropentane, don't worry about that, that's obviously from 1B or 1A. This reaction gives phenylethanone as the main organic product. So let's go through. There is the benzene reacted up with ethanol chloride right there, the eth telling you 2 carbons, and gives you phenylethanone as the main organic product. What's happened when some drops of phenylethanone added to a solution of 2,4-dinitrofenylhydrazine? Anytime you see 2,4-dinitrofenylhydrazine, you know that you're looking at the test with carbonyl groups, either aldehydes or ketones. We have a ketone right here, so therefore we're going to make the nice complex. Ketone, of course, double C double bond O, reacts with a primary amine there to give you the imine. Okay, and this, of course, is going to be a nice solid that will probably, because you've got an aromatic group here, be a ready orange precipitate. Much more importantly, of course, for DNPH is they have very diagnostic melting points to help you identify exactly what is on here. As we know what's on here, all we need to do is just say we make a red orange precipitate. So to test for the presence of iodine in an organic compound, first of all, you heat the compound with aqueous sodium hydroxide. This, of course, substitutes the iodide for the hydroxide, leaving iodide floating around the place. Okay. We then add nitric acid. The nitric acid is going to be to neutralize all of the sodium hydroxide. And then once we've neutralized that, we've got some iodide floating around that was kicked out by the hydroxide. And a good test for iodide, as with any halide, is adding silver nitrate to it. If iodide was present, in other words, if iodine was present here that then got booted out of it, well, then you'll get a precipitate of silver iodide, which is a yellow one.